All right, everybody, it's time to round out our learning for the covalent bonding unit. We are going to talk today about intermolecular forces, or IMFs for short. So these are the forces that are found between molecules, and these are the forces that we have to overcome if we want to melt or boil something. So if we think about water, right, water's H2O, I could draw H2O like this. When I boil water, I am not attempting to break this bond, right? This is not a chemical process, boiling. Boiling is a physical process. What am I doing? Well, I'm breaking the attraction between the green water molecule and the red water molecule, right? So there is a force we'll talk about here today. There's a force that's attracting those together, and we are trying to break that. So the strength of these intermolecular forces gives rise to a lot of properties in terms of high and low melting and boiling points and how strong these things are held together. Just a heads up, inter is a word that means between, so interstates go between states. Intra means within. So the bonds we talk about are like the intramolecular forces, where these are intermolecular forces, they go between molecules. There are three types: dipole-dipole. Hydrogen bonding is a special type of dipole-dipole, and then London dispersion forces. If you wanted to pronounce this with an English accent, we absolutely, we encourage that for sure. So let me give you a brief little discussion of the energy or the strength of these. So if we had down here, if we had really weak things down here, and we had a continuum all the way up to strong things over here, let me spell strong correctly, then we could place our bonds somewhere along this continuum. And our bonds would be up here, right? So we would have covalent bonds, ionic bonds, metallic bonds. We're not going to ask you to distinguish between the strength of those different bonds because that's a difficult thing to do and it depends on what you're bonded to. And all the way down here are these forces. So these forces are way weaker than bonds in general. And at the bottom of this list is LDF, London dispersion forces. And just a little bit stronger are our dipole-dipole. And of dipole-dipole, the strongest force is called an H bond or hydrogen bond. Now, couple things. Notice that those three are way weaker than any of our bonds, right? So these things are a lot less strong. Now, we can talk about their strength relative to one another. So certainly hydrogen bonds are much stronger than London dispersion forces, but they're still way weaker than actual bonds. And the other thing that's confusing here, as a teacher, we get very frustrated with whoever named these. This is not actually a bond. It's called a hydrogen bond, but it is truly an intermolecular force. It is a force between molecules, not within them. So that's very confusing, admittedly, but don't think of it like covalent and ionic bonds. It's a completely different thing. It's a force between different molecules. So let's talk about these. First off, dipole-dipole forces. Dipole-dipole forces occur when a dipole is formed. Now, when is a dipole formed? A dipole is formed in a polar molecule. Remember, in order to have a polar molecule, you must have either lone pairs on the central atom, or you must have polar bonds to different atoms. If you have polar bonds to the same atom, like carbon dioxide, you have a non-polar molecule. So we need to have polar molecules. And a dipole-dipole force occurs when you have these types of attractions. So, for instance, if we had water, actually, let me not do water, because, well, we can do water. It's a special case, but let's have water. Water has a very electronegative oxygen and some not so electronegative hydrogens, which means it gets partially positive and partially negative charges like so. And I could draw another water molecule down here that has similar partially positive and partially negative charges. And that gives rise to those dipoles that we talked about. And so what that means is that we have a partially negative near a partially positive and a partially negative near a partially positive. And so that attraction is what we refer to as a dipole-dipole attraction. Now, the reason I was hesitant to draw water is that this attraction that I've drawn for water is actually a special kind of attraction, because it turns out that when you bond hydrogen to some certain atoms, it has a really big difference in electronegativity with atoms like oxygen. And so the polarity of this bond, the polarity of this hydrogen-oxygen bond is actually very, very large. So dipole-dipole is a term for the type of intermolecular force that occurs with polar molecules. But if you happen to have a really strong dipole, one that is really strong relative to others because hydrogen is involved, you call that a hydrogen bond. So here is an example of a really strong dipole-dipole force called a hydrogen bond. It's the same one as water. You'll notice we again have the partial positive, partial negative charges, and there's an attraction between this partial negative and this partial positive, right? They want to be together. Same thing with this partial negative, this partial positive. They're lined up together. Now these are special cases because it turns out that when you bond hydrogen to 3 types of atoms, either nitrogen, oxygen, or fluorine, because all of those atoms are small, you'll notice they're all in the second energy level, and hydrogen's in the first energy level. Because they're all small, that means they have a big electronegativity difference with hydrogen. So those 2 factors, big electronegativity difference with hydrogen and the fact that they're small, means that the polarity of the bonds between N and H, between O and H, and between F and H is really big. And so that means that there's a really strong attraction because the partial positive and partial negative charges are a bit stronger than they'd be in a normal polar bond. So hydrogen bonding is a special case. It's the strongest case of intermolecular forces, strongest case of dipole-dipole. It occurs in molecules that have a hydrogen bonded to nitrogen, or a hydrogen bonded to oxygen, or a hydrogen bonded to fluorine. So you can see in both of these cases we have hydrogen bonded to fluorine, or in this case I have hydrogen bonded to water. So those are both examples of hydrogen bonding as opposed to dipole-dipole that would take place in simply a polar molecule. Our last type is, oh, and one little note about that, hydrogen bonding, this is a picture of water as ice. So the fact that hydrogen bonding is so strong means that water can actually hold itself in this rather rigid structure with these pretty large gaps in it, which gives rise to the fact that ice is actually less dense than liquid water. And it's one of the only substances for which that's true. Most of the time, solids are more dense than their liquid counterparts. So our last type is London dispersion forces. London dispersion forces occur in non-polar molecules. And I've been trying to make the point in this video that the reason we have these little attractions between molecules is because we have partial positive and partial negative charges lining up near one another, and there's an attraction between these two. So if you're really thinking hard and you're thinking about nonpolar, nonpolar by definition means that we don't have partially positive and partially negative charges. So what the heck? Why is there an attraction between nonpolar molecules? And that's a great question. And the reason, or part of this that we should talk about, is the fact that these are really, really weak attractions because they're so fleeting. There isn't a partially positive and partially negative charge. So imagine this. I'm going to draw out a couple of hydrocarbons. Imagine you have a long hydrocarbon chain, and I'm going to draw it like a zigzag like this. Just imagine that this is every point representing a carbon, and there are hydrogens hanging off the carbons, right? And so we have these 2 chains next to each other. And those chains are really long, right? And so imagine for a quick fleeting instance, and I'll draw this with this highlighter. For a fleeting instant, what if the electron density got pulled down towards the bottom of this chain, just briefly? Right, so it's all down there to the bottom. And what if at the same time we had all of the electron density of the purple get pulled down toward the bottom as well? Right, so that one is a little bit partially negative down here, and this one is a little bit partially negative down here, which means up top is partially positive, and up top here is partially positive. And lo and behold, look at what we have. We have a partially positive next to a partially negative. The thing is, that doesn't happen very often at all, right? So this happens for like a fleeting, way less than a millisecond. And it turns out that it acts a little bit like Velcro, right? So if you had a piece of Velcro that was half an inch long, it would be pretty darn easy to rip up. But imagine that this hydrocarbon is super, super long. You could have this situation going on here. It could happen here. It could happen here. It could happen here. Essentially, you're making your Velcro piece long. So what if you made your piece of Velcro miles long? Now you'd have a situation where you have a ton of these fleeting interactions, and all of a sudden those chains are actually held together just a little bit more than you might have expected. And so that's what a London dispersion force is. It's this fleeting occurrence where you have the dipole, not the dipoles, we don't have any polarity going on here, but we have the electrons move in such a way that the electron density is shifted up or down just slightly in these nonpolar molecules, and that allows them to stick together. And so it turns out this is very dependent on the mass of the molecule, because the heavier the molecules, the more interactions there are. Why is that? Because heavier molecules are longer, right? So the longer the molecules, the more interactions. And you can actually experiment on this with boiling point. So it turns out that molecules that are really long, even though they're nonpolar, have much higher boiling points than their shorter counterparts. And that is because when we boil them, we're trying to break these interactions. So the more interactions, the longer that Velcro, the harder it is to break, and therefore the higher the boiling point. So let's see if we can get some practice assigning these types of intermolecular forces to the molecules that we've already drawn. So we need to ask ourselves whether we are dealing with a polar molecule or non-polar molecule, right? So let's do that first. You'll notice in PCl3 we have a polar molecule. If it's a polar molecule, we are dealing with either a dipole-dipole IMF or a hydrogen bond. In order for it to be a hydrogen bond, we need hydrogen bound to NO or F. There's no hydrogen in this molecule, so this is going to be a dipole-dipole intermolecular force. Over here on the right, again, if it's polar, then we have a situation where we're either going to be dipole-dipole or hydrogen bonding. In order for it to be hydrogen bonding, we need hydrogen bound to NO or F. You'll notice hydrogen is not bound to any of those. It's bound to carbon. So really the only thing that's causing polarity in this molecule is the CCl bond. So this again is dipole-dipole. We don't have hydrogen bound to NO or F. In carbon dioxide, this is nonpolar. So nonpolar automatically means that your intermolecular force is a London dispersion force right off the bat. It's the only intermolecular force present in nonpolar molecules. Here we have a polar molecule. We do have a hydrogen, but again, it's not bound to NO or F. So our choices are dipole-dipole or hydrogen bonding. This one has to be dipole-dipole because our hydrogen isn't attached to an NO or F. Yes, there's a nitrogen in this molecule, but hydrogen is not bound directly to it. We have a polar molecule in O3, but we don't have any hydrogens here. So it can't be hydrogen bonding, it has to be dipole-dipole. And then down here in NO2, we again have a polar molecule and we have no hydrogen, so we would think that this should be dipole-dipole. But there's a trick lurking here. Intermolecular force means between molecules. There is really not a molecule here because it is an ion. And the force that holds ions together is a little bit different. The force that holds ions together is the fact that they have a full-blown partially positive or partially negative charge. So this full-blown negative charge is going to attach to another full-blown positive charge, and so the IMF here is really ionic. The force that is holding that ion to another one is not a dipole-dipole attraction, because the ionic force is way, 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 way stronger. It's an actual bond that's holding it as opposed to some sort of dipole-dipole interaction. Okay, let's try two more. Let's see if we can identify the intermolecular force present in these two molecules. Let's do water. We again need to draw out its Lewis structure. We can get some refreshing of our memory here, right? So water has two hydrogens. Each hydrogen has one valence electron. It has an oxygen that has 6 valence electrons, so that gives us a grand total of 8 valence electrons. When we draw our water in, we're going to put oxygen in the middle. We need to put on more lone pairs. We need to show 8 total electrons. We can't put any more on the hydrogens because they already have 2. So we will put 2 like this and like that. This is actually misleading with water. If you've seen me draw water over and over again, you'll notice that I keep making it bent because the lone pairs actually do that up top. That's another shortcoming of Lewis structures. It makes us think that this thing is shaped differently than it actually is. Again, we'll make a model in class. But if we want to assign polarity, we first have to ask ourselves, is this polar? And yes, it's polar because we have a lone pair on the central atom. So yes, this is a polar molecule, lone pairs on the central atom. If we're trying to assign polarity, it either needs to be dipole-dipole or hydrogen bonding. Hydrogen bonding is when we have an H bound directly to N, O, or F, and you'll notice we have H bound directly to O, so the IMF in this case is hydrogen bonding. Feel free to go through and draw your Vesper model and things of that nature as well. Just as an aside, this would be AB2E2, which would mean it would be bent. Let's try carbon tetrahydride. So carbon tetrahydride is carbon. There's one of those. Carbon has 4 valence electrons. That gives us a grand total of 4. Hydride is short for hydrogen. There are 4 of these, each with 1 valence electron. There are 4 more, so we again have 8 valence electrons. We are going to surround our carbon with 4 hydrogens, like so. You'll notice that each of those bonds represents 2, so all of our hydrogens have their full duet. Our carbon has its full octet, and we've already represented all 8 electrons. The carbon-hydrogen bond is nonpolar, plus we have bonds to all of the same atoms. So for 2 reasons, this is a nonpolar molecule. And anytime you have a nonpolar molecule, automatically, right off the bat, you know that it's going to be London Dispersion Forces, or LDF, as your intermolecular force. And if you want to take that a step further, this is going to be AB4. It's going to be tetrahedral. It's going to be 109.5 degree bond angle.